our next distributed information systems lecture, again in online mode. A quick reminder, during the lecture, the cameras are optional, and during the exercises, they are mandatory. So you need to turn up your video cameras inside the exercises. And I've heard that there would be some problems with people grouping and missachten. Not taking into account corona measures, just blur your background and get some more distance, and then no one will recognize that. So what do I wanted to do? I wanted to do something. Let's first of all share a screen. I'm currently trying a new headset, so if I'm dropping out again because of a battery problem or connection problem, please inform me. So, but we will first share a screen, then Teams will minimize itself as always. No clue why it does that. So main screen is shared. So last time we met, we were talking about some basic aspects regarding distributed information systems, talking a little bit about transparency, and next step would have been openness and scalability. But due to the fact that we are going to have an exercise this afternoon after lunch, we will just swap some slide packages. So we will postpone the discussion about openness and distributed information systems and get right to the stuff we need after our lecture and our exercise. Perhaps we'd first talk about the exercise itself, very short introduction into the exercise, and then we talk about what aspects we need in order to solve them. So today we start with the general exercise, and of course we start at the beginning with exercise 1, and exercise 1 is establishing a communication between a server and a client class using sockets. And we start with the C++ side, and once we have a fully working C++ side, we will connect a Java or build an equivalent Java version, and then connect the Java socket client to the C++ server. And then everything works out smooth and nicely. And this will be one of the larger exercises. And the exercise is a step-by-step approach. So you start at the beginning, and slowly the system gets refactored and gets more powerful, and more features are integrated. Yeah, you will see that in a moment or two. So first of all, there are some remarks. Visual Studio only. So this piece of code is only relevant for those of you who use Visual Studio on a PC or a virtual Windows on Mac. So then you can use this piece of code to begin with as a starting point. For those of you who work with C-Line, this piece of code is relevant. And for the ones that are using Xcode, sorry, no Mac user, I have no option for you, but it should be quite similar to the C-Line stuff because it's quite low level. If you use C-Line on a Windows PC, please install Cygwin. And when you install Cygwin, you should install CMake, GCC Core, GCC G++, and libgc1, the GDB debugger, and make. They should all reside in the development categories. And once you install that, and then you need to manipulate your, let me get this into the screen. And you need to manipulate settings, come on. Settings, genau, build, execution, and deployment in the tool chain. you switch to the Cygwin toolchain, and then this should look like similar like this. So you have a environment Cygwin, CMake, make, everything should be from Cygwin, and everything should have nice little green arrows. Then we know you have a system that should work with the exercise, okay? And after that, you can copy the source code fragment of the C-line introduction into your project, and then you can start later on. That's basically it. So
that was now the procedure for C-line on Windows. Is there anything to keep in mind for Mac?
No, I already said that. Sorry, I'm no Mac user, but it should be quite similar to the C-line version.
Yeah, C-line is available for Mac. Yeah, but do we still need the Cygwin?
No, the Cygwin, you don't need Cygwin because it's for Windows. Sorry, I didn't get your question right. No, Cygwin is not necessary for Mac users. They should have installed it. The Mac system typically works without any problems. The only problems the Mac system makes is when we get to the semaphores and stuff like that. So multi-threading.
Okay.
Aside from that, this is just for the Cygwin is just for the Windows users. Okay, sorry if I didn't state that. So once we have our system up and running, we get to the tasks, and there are quite a few tasks, and some are marked with an O as optional, meaning if you have already worked with socket communication on a C++ C level, you can, but you don't need to make these tasks in order to build a working system. Nevertheless, it is regarded that you should work on them. It's not bad to start from scratch and let this socket communication be revised in another time. So we start with task 1.1.a. And what we do is we build two C++ programs, and they just consist out of the main function. So there will be a server main and another project, a client main. And we first integrate everything into the main function, which of course is not object-oriented at all. But we first take into account the connection, the communication, and once we are sure that the communication between these two programs, these two processes is working, then we refactor the system and establish an object-oriented version of our communication, and then extend the program further. So in the first few steps, we will have some rather dirty code, but that's on purpose because we are concentrating on the socket part and not on building nice looking code. And once we are ready and already know how this socket communication works and what needs to be taken into account, then we make our code beautiful and nicely organized and stuff like that. So beginning with today, we have two programs, two projects, the server and the client, and they should connect to each other via a TCP/IP socket. And in the first step, only the connection is relevant. So we have two programs, and you will later see the server gets started first. The server is in a waiting state, waiting for a client to connect. Then we start the client. The client initiates itself and then connects to the server. The server realizes, oh, there has been a connection. Then the server is happy, shuts down, the client shuts down, everything is fine. So we are in the first step are just concentrating on the connection itself so that they are able to connect, no communication yet. And in the following steps, we will integrate the communication between both of them. First step is just connecting. So that's basically the first step. What you should always do to take into account possible error conditions. So this is also something I stated last time we met, the aspect where I can reduce your still perfect exercise counter. So if you ignore return values, and that's bad coding, and therefore I can reduce your 100% state. But I'm inside the exercise, it is stated that you should take them into account, and take them into account in a useful manner, not just, there's an error, I ignore the error and continue, but you should do something useful when you realize there is an error. So when we have successfully built the two programs and the two systems connect to each other, then we refine our program first by transferring the communication port. We will see that when we have a socket communication, we typically need a communication port that is used to establish the communication. And this port in the first step is hardwired. And in the second step, we provide the communication port to the client and to the server part through a program parameter. So we need to work on this program parameter. So in the main program, this parameter is provided by the system. At the second place of the values of the main function, and we extract the port and then use the port provided. And when we additionally in the client program, we also provide the server IP address, so the IP address of our communication partner. So on the server side, only the port is provided. On the client part, the port and the IP address of the server is provided. And of course, if the values are not present, then some kind of user manual should be printed out on the console, and the program should be shut down or restarted. The read-in should be restarted until the users entered something useful. When we have done that and everything is working, so after every refinement, you of course test your system. And the last refinement will be when the connection is established. So when the client is connected to the server has the ability to read out the information which client is connected to the server. And this information should be used and printed out in an appropriate way on the console. So the server should state our client IP address is connected to me at port, and then the connection is shut down again. So again, only connecting, no communication yet. Next step, 1.1c, is then the final refinement to really establish a communication. So this refinement first starts with the client side, and the client side will get the ability to read in a complete line of text from the command line of the client side. And when the text is read in, it sends the content to the server. The server itself reads the data from the socket, of course, and prints it out on the command line. Something like, okay, client send, and then whatever the client sent to it, to the server. So this is the next refinement. Again, always test your system after each refinement step. Next step is the server does not quit when the client aborts and the connection. So the client first reads in a statement, sends it to the server receives it, and the client shuts down. And in our first situation, when the client shuts down, the server also shuts down. This should not be the case anymore. So the server should go again into an accept state, waiting for the next client to connect. So the server is running at this point in time forever. Next refinement is not shutting down the client after the first communication, but keeping the client alive for as many communication intervals as you like. And the client should also receive some data from the server. So the client reads in a line of text, sends it to the server receives the text, prints out the text, and then sends back an acknowledge command to the client, telling the client, okay, I received your message, everything is fine, you can send the next message. So that's basically the idea. Then you should extend your system by integrating a quit command for the client. So when the users write in quit, the client shuts down gracefully, meaning that the client closes the communication socket and then closes itself. Gracefully means that the connection is not disrupted without any interaction, which can also happen when the server is shut down and the communication port is shut down by Control C, or because the IDE has been closed. Then typically the underlying socket library does not realize that the communication has ended and keeps alive some ports, which is typically not the best thing. But the operating system cleans up the mess after a few minutes, typically. So the quit command, which can be read in by the client, closes the client gracefully. And when we print shutdown on the client side, and when the shutdown command is sent from the client to the server, then also the server shuts down gracefully. And then basically we have client-server communication that is quite nicely working. Was there a question, Herr Steiner?
We are working with two programs called server main and client main, and further refine it, all the steps. Should we always, when we finish one iteration, so-called, from task A, save it like 1.1, then make another one, or should
No. Give me a second. I will check later on what the functionality is of the overall system. And when you later are able to have a communication between a Java Java socket client and a C++ server, I believe that you follow these aspects and follows these steps. So you will. Okay, my connection dropped for a second. Can you still hear me?
Now again, yeah.
Okay, so what was the last thing you heard?
We're established, but I get the point. It's just a little, take me by your hand and show me how to do it a little bit there.
Yeah, in small steps. And when you are able to do the big leap, then of course I believe that you can do the tiny steps as well. Nevertheless, there will be some optional stuff which you don't need to do in order to have a fully working system later on. And of course, I will check that. So we will have some UDP communication, some synchronization mechanisms, which are just playing around and which are not necessary for the overall system. Nevertheless, they are part of the exercise. And if time runs sparse, you can do them or you can drop them. And then when you drop them and I check them, then of course I get the equivalent of the percentage of your 100% perfect score. But you will see that. So the beginning is typically warm up, as we call it. But it's a useful warm up if you never did socket communication, or if you just did it once or twice. Better do the warm up and not run into something unexpected. Something that happens when a socket is not closed gracefully, not informing all the other communication partners. Typically, as I said, the socket library does not recognize or realize that the communication has ended because there are some blocking functions integrated, and it believes it's just waiting, actively waiting. And therefore, these ports may be blocked. And when you want to restart your program, the system tells you, oh, sorry, I can't establish the socket at this port because it's already in use. And then you have different solutions for that. You can either choose a different port. So when you start with 5001, then you use 5002, 5003, 5004, and so on 5. And after a few minutes, typically the operating system realizes, okay, this is dead. I can clean it up. And then you can start with 5001 again. Or you can choose to kill the process that is still holding the port blocked, and by using a certain bash command, or in this case, this is for Windows PCs, you can kill, or you can find the process that blocks the port, and then tell the system to kill it, and then the port is unblocked again, and you can restart your program without any fuss. The next step is further refinement, but typically for today, first the warm-up aspects are enough workload. If you should already finish the warm-up today without any problems and still have some time, you can contact me, and then we talk about the next steps and see what you can manage with the rest of the day. Okay, so that will be the part of the exercise we will be talking about today. And I have to inform Michael that I already did an introduction, because I told him on Monday that I will do that, perhaps not do that, but I changed my mind yesterday, and therefore he doesn't need to do the introduction. Or if you want for automotive computing, if you want another introduction into the exercise, you can of course tell Michael to tell you what's going on. Fine, so let's...
Herr Professor?
Ja, Höhner.
Im Stundenplan, wenn ich zum Beispiel in den Nachmittag gehe und draufklicke, dann steht dort nicht, mit welchem Professor. Also haben wir Sie dann in der Übung, oder?
Aktuell, wie ich es eingangs mal erwähnt habe, habe ich sämtliche Mobile Computing Kurse, und der Plattner hat den AC-Kurs, also die AC-Übung. Ja. Wenn die AC-Gruppe möchte, dass ich da auch mal reinschaue oder so, oder dass wir das alternieren sollen, dann brauche ich dann entsprechendes Feedback, damit wir Pia triggern können, dass sie das ein bisschen durchmischt. Das muss aber von Ihnen ausgehen. Im Moment haben wir es halt so aufgeteilt. Mir ist es völlig egal, welche Studierenden da sitzen.
Also uns AC, glaube ich, trifft es gerade voll, weil noch nicht gehört, also TCP und sowas haben wir ja schon Gott sei Dank gemacht einmal. Aber wir sitzen alle gerade ein bisschen so da, aber wir vertrauen auf den Platte recht gut immer.
Okay, passt. Er wird das so hinkriegen, überhaupt kein Problem. Und wenn irgendwo ein Problem sein sollte, was nicht zu lösen ist, dann können Sie sich natürlich kurz rüberblenden, und dann schaue ich auch mal drauf, okay?
Passt.
Optimal, dann machen wir das so. Right, after this chatting, some input into BSD sockets and how to do them. As I already said, we will be doing socket communication on a very, very low level, so no socket class, which are, of course, available in modern C++, but we will use the low-level versions in order to get our hands a little bit dirtier than the usual. So what's the motivation for the communication? As you all know, we typically have a communication between some sort of client and some sort of backend system. Give me a second. Why is... ich hasse diese... Give me a second, because it's not turning... macht diese Laserpointer-Geschichte hier nicht in diesen Bildschirm rein, aber jetzt richtig. So, genau. So we typically have a communication of some sort, because everything we do is somehow connected with the internet. We do the lecture with the internet, we communicate with our social media platforms, with the internet. And typically, so we are typically a client and we want to do something. And in the background, there is some kind of server infrastructure, cloud-based, system-based, whatever you can think about. So the client communicates with the server. And the most used communication form is via sockets. So I would say 95% of our communication with the internet is, even more, is based on socket communication. So every time you use a REST service, every time you use a web browser, it's always socket communication in the background at the lowest level. And therefore, this is also something we have to take a look at. Another thing that is important, the client typically is the one that wants something from the server. So the server is the one that provides some kind of service. That's the reason why it's called server. So it provides services, and it's the dormant, the waiting part. So the server is started, provides some kind of service, and waits for one or multiple clients to connect to itself and trying to use the services the server provides. And this is also the way the socket communication later is working. There's a server socket and there is a client socket, and the server socket is waiting for a connection, and the client socket connects to the server, and then the connection is established and everything starts working. And this is basically the communication pattern we will be using and in our system. So what are sockets? When you take a look in the literature, the sockets are defined as communication endpoints to receive and send data over a network. So that's basically the primitive definition of a socket, communication endpoint. They have been designed in the early 80s and at the Berkeley University, and they integrated it into their Berkeley software distribution, some kind of Unix. And the nice thing is what they envisioned in the early days of the internet is even used today. And therefore, when we play around with sockets, we quite often still use the acronym BSD sockets, so Berkeley Software Distribution Sockets, because the idea how this communication should work is still similar to the first envisioned situation. And of course, there are some improvements have been made, but basically the design principles are still the same. What can be said about sockets? In the background, they use data streams. So there is a stream of data, a stream of sorted data. And sockets use, as I already stated, the client-server communication pattern. So there is a server that offers services, some kind of resources, and it is waiting for clients, for customers wanting to use its services. And the client wants to use the services and wants to use some resources of the server. And in order to do that, the client needs to know where the server is and how to reach the services. So in order to access the services provided by the server, it needs the IP address of the server, and it needs the address of the service that is residing on the server side. The address of the server typically is the IP address. We will start with IP version 4 and then later on extend our system to support IP version 6. But in the beginning, IP version 4 is typically enough. It's a little bit simpler. It's some of the used structs we will have to integrate. And therefore, we start with IP version 4. And then later on switch to IP version 6. And then at some point we can support both of them. Right, so the address of the server, the machine of the server can be accessed by the IP address, and the address of the service can be accessed by a specific port, some communication port. Taking that into account, when you do your exercise, typically you start exercising that on your own PCs. So even if you have teams, every team member tries to build a client and a server. And when the client-server communication on one machine works, you typically try to reach the server of your teammate. And due to Corona, this can be problematic if you can't meet with your teammate, if you don't have an open IP address. Then we have to live with the situation that you just try to do it on your own PC and try to reach your own process that is residing on your own PC. If you have an additional computer available, like a gaming PC or a Raspberry Pi, of course, you can use this machine as a client or a server and then really play around with two different machines residing in the same network, which of course is more realistic as a test scenario. But as we are in Corona's mode, we have to cope with some additional difficulties, but we'll manage. So taking a look at the communication types available for sockets when we use IP address version 4, which slightly differs from the IP version 6. We have 4 different communication types. We have at the one hand the stream-based communication, which uses fixed communication connection, which is quite important. So when the client communicates with the server, they are connected, and this connection stays alive as long as the communication is established. This is important to be taken into account. This brings us some good features and some bad features. The good features is there is some kind of error correction automatically supported, but of course this automatic doing something automatically in the background typically provides causes some overhead. So the stream-based fixed connection is typically slightly slower than the unfixed datagram communication, which is the second one in this list. But you will have to experiment with both versions, so no problems. We will take a look at all of them. Not the broadcast stuff, but the basic communication. So we have a fixed communication between 2 endpoints, 2 sockets. And the nice thing is that this byte stream that is sent around is ordered, which gives you first byte that gets in, gives the first byte that gets out, which is important when you have to reconstruct your message from a byte array. Yeah, in the background, the protocol, the library decides about the packet size. Of course, the system doesn't try to send one byte after another over the communication network, which would be completely not suitable, not a good idea. So the system in the background decides, okay, how big the chunks are that are sent in one go, and therefore in the background it is of course not a continuous stream of bytes. It just looks like from the parts where we use the socket. So we put in one stream in the client side, the stream goes into the socket, then is chunked into some packages. The packages are sent over the network, pops out at the communication partner side, and then a complete stream of bytes is again re-established, and from the both sides using the socket on the client and the server side, it looks like a stream. And this is basically the TCP version of a socket. Then we have the datagram version of a socket that is using a connection that is not fixed. So what you do is somewhat comparable to the postal office. We know from a day-to-day basis. So when you want to send a real text, hardware, paper letter to your parents, you put it to the postal office, and the postal office tries to send it to your parents. And this is quite similar to the datagram version of the communication. You build a datagram, pack some data in a package, and then send it into the network and hope for the best. The problem is, of course, there is no error correction, automatic error correction. So you hope for the best. If the communication network is fully under your control, typically these hopes can be quite realistic. And the further away the communication partner gets, this is also something we talk about in the basics later on, the more unstable this communication gets. And then it can happen that some packages are dropped, that some packages are choosing different communication ways. So the package sent later is received earlier than the other one. And if you want to rebuild the data you integrated into these packages, you have to, of course, keep the order of the packages in line. And this is then something you have to take into account, and which is not done automatically. Right. Broadcast is that you send some data to all the network participants, which of course is something you only do if you know what you are doing, because otherwise you are wasting precious network bandwidth. And multicast is similar to broadcast, just to a specific group of clients on servers in the system. But we will concentrate on this on the stream and datagram-based versions. So in conclusion, we will use the TCP sockets and the UDP sockets, and primarily we use TCP, the short version for transmission control protocol. It's a datagram protocol. Transmission control protocol already states it. There is some kind of control established in the background, which is, of course, a nice thing from the programmer's perspective, because everything we don't have to do is something some time we gain. This looks like it is stream-based. It is a connection-oriented protocol, meaning that the client and the server are connected to each other, and this connection stays as long as the communication is active. We have a data flow control. First byte in is the last one, is the first byte that gets out. We have some kind of error handling. If one of these chunks in the background is lost, the chunk is re-questioned by the system in the background. We don't get anything, or we don't see that in the on the using side. And so the system automatically takes care that everything comes in one piece and in the right direction, in the right order. As I already stated, this costs us. There is some overhead involved. The package size is reduced because we need some overhead data to make sure that everything comes as sent. And therefore it's slightly slower. Nevertheless, TCP is one of the most used versions in our world today. If you want it to be a little bit faster, but a little bit less secure, you can choose to use the UDP communication. So that's datagram based, just like a postal letter. You pack in some data, throw it into the network, and hope that it is sent to the communication partner. And in an internal network, this typically works nicely. And the larger the network goes, the more problems arise. So you don't have a fixed connection. You don't have, or you have no guarantee at all that the packages will arrive. And you have to make sure that you check, okay, is this the package I received? Is this the first package of the data? Or is this the third? What about the second? Why don't I have a second package? How can I re-request package 2 from my communication partner? All that stuff. So this brings more workload to our side, establishing the communication. But due to the loss of automatic something in the background, it is faster and provides nearly no overhead. So depends on what you want to achieve and how important these packages are. What we now do is take a look at something I call support methods. These are methods we will have to use later on in our exercises. These methods are all available on all the systems. On the Mac and Linux side, they might sometimes look slightly different, but very, very similar. You will all be able to find them. And all these methods are available. You don't need to recode them. This is also something 2 to 5 persons in this lecture will try. They will try to rebuild the structs I present. And you don't need to code the structs. They are available. You just have to use them. So be careful. You can try to copy and paste the examples, but you should not try to copy and paste the definition of the structs and the methods. They are available, okay? So first support methods we will take a look at are these nice little H2NL, H2NS, host to network long and host to network short, converting the byte order from the host byte order to the network byte order, and backwards, network to host long, network to host short. That's the little versus big endian problematic. So when we want to put some information into the socket aspects, we typically have to do some conversion, especially when we want to tell the socket which port it should bind itself to. Then we need this host to network short, and then we need to convert the port we are writing down, of course, in host byte order, so it will be transferred into network byte order. Right, that's the first 4 methods we will use. We will concentrate on H2NS and N2HS because we will be just playing around with shorts, but of course there are other ones as well. Then we have something that helps us convert an IP address into something humans can read and something machines can read, and backwards. So the eNet address method provides a version 4 IP address in network byte order based on a character array. And at some point we want to define the address of our server, or we want to, that's basically the main aspect we want to do. We want to reach a server that is reachable under this IP address, version 4. And this help method, this support method converts it that it can be used inside a socket mechanism. Herr Steiner?
The H2NS, which means short, is the little endian, so-called, then. Or has it to do something with large and short to little and big?
No, it's just a long value and a short value. So integers long,
okay.
Basically like that. So that's the idea. And it's always host to network. So we don't care which which byte order our system uses because the methods do the conversion the right manner. If there is no conversion necessary, the system will do nothing, but we can still call it.
Okay.
So we're on the safe side. And the nice thing is that when we have this code and when we have coded it rather low level, we can copy it to a different hardware platform, compile it, and it will work on that system as well. Okay?
Yeah.
So always make sure that you use them if you need to use them, and you will see later on where to use them. So iNet address converts something we can read into something the socket needs. And the other way around, eNet N to array, N to A, which provides us with this typical 4-block byte order information of an IP address based on something we extract from a socket. And there are 2 versions of this convert the IP address into something I can read, some with error handling and some without error handling. So this one is the old version, which has the problem. This version here is the one that has no error handling, because when it returns a -1, then this -1 also represents a valid IP address. And as this can be problematic because you are asked to check if errors occurred, then you cannot identify the error. And therefore, there are different versions of this conversion mechanism available inside the different libraries. And some of them provide some decent return values, which tell you, okay, an error occurred. You cannot use this conversion aspect. And this one is the error safe version of this one up here. And the next slide shows us a version that is also capable to later work with the IP version 6 aspects. But when we come to the IP version 6, as far as I remember, I repeat the Piton and NTOP version, which are on this slide, and the next one again. So this P to network and network to P converts an IP address stated in textual form into network byte order. And as you can already see with the signature of this method, we have something very dark and very dirty back lurking here, a void pointer, which typically means, okay, anything can be put in here. And the system decides based on what flag you provide at the beginning, how big this in the back is and how big this one is. And therefore, it is really, really, really that important that what you state here matches